All right, in this video, we're going to look at some examples of how you place various shapes on a coordinate grid to use coordinate proofs. And so we're going to do a couple examples about rectangles because rectangles are interesting. And there's two ways to do it. There's actually multiple ways to do a rectangle. So let's talk about two, and then I'll suggest a third way as well that we could do. The first way is to take advantage of the right angles and essentially place your rectangle with one of the vertices at 0, 0. And then another vertice along the x-axis. And so it would look like this. Remember, we use 2a instead of a as our variable just because it makes our life easier usually. All right, so what this has shown is that we've got this segment AB, and that has length 2a. Now, there's a second side to a rectangle, and we don't know how long that side is. And so, but we're going to take advantage of the right angle and putting it up against the origin. And we're going to say that this point, D, is going to need to be 0 over and 2b up. So when you're doing these, you pay really close attention to distances and lengths, especially when you can do them easily along the lines of the coordinate grid. And so we know this length is 2b, and we know this length is 2a. And so our fourth point, the one that goes right there, well, it must be 2a over and 2b up. And so its point is just simply going to be 2a for the x-coordinate because it's on this, it's straight up from b. And then since it's straight over from d, it's going to be 2b in the y-coordinate. So these 4 points, 0, 0, 2a, comma 0, 2a, comma 2b, and 0, comma 2b form a rectangle. And we know it forms a rectangle. Now, the other way you could do it, what some people like to do, is to use the symmetry of a rectangle. And the symmetry of the rectangle says that we could put the point where the diagonals intersect at the origin. And if we do that, what we could do is we could call this one up here a comma b. So just placing it some random distance. And then essentially saying this length is a and this length, or actually I got it backwards. This length is a and this length is b. And the reason that's good is you could do that in every of the each of the four quadrants like that. And so this would give us, well, still a over, instead of positive b, negative b. This one would be, well, they're both negative, so negative a comma negative b. And then up here would be negative a, but then positive b. And so those four coordinates would, in the same way, form a rectangle on a coordinate grid. In this case, the side lengths are the same as the last one, which is 2a and 2b. All right, a couple more examples. We could do a kite. And so to do a kite, we're going to utilize a really useful thing about a kite when it comes to putting it on the coordinate grid, and that is that a kite has perpendicular diagonals. And so our point that we're going to use is the origin, but that origin is going to be where the diagonals intersect each other. And if we remember, when we draw a kite like this, we remember that the vertex diagonal, the one that's going to connect our point, we'll call this point A, the AC, the vertex diagonal, because we're going to do it like this, where it looks like those are the same, it bisects DB. And so that's one of the really nice things is here, if I let this point be 2a comma 0, then the point over here is going to be negative 2a comma 0, because AC bisects DB in a kite. We know that, and we've shown that in a kite, the diagonals, the vertex diagonal bisects that base diagonal. Now, up here, if we let this point, it's going to be 0 comma 2b. It's some distance away, some distance above that point where the diagonals intersect. And then C is some distance below it, and we don't know how far below it is. We just know that it's different distance than the 2b. Now, You could either do this one. Some people like to call this negative 2c, and let 2c be the actual distance, the length, or you could call it just 2c, and so in that way 2c would have a negative value based on where it's placed. It doesn't really matter when it comes to proving things with a kite. Now, you can do a kite in some other ways as well, using some of the same properties. You could put a kite like this if you wanted, right, where you're, and that would be fine. It's just not quite as simple as the one that we did over there. All right, last one here is a parallelogram. So when we use a parallelogram, we're going to start it like we did the rectangle, the first rectangle, and then the quadrilateral we did in the other video, in that we're going to put the coordinate at 0, 0. We can't use the right angle like we did for a rectangle or for a kite. The symmetry isn't there for that. And so what we're going to do instead is we're going to take advantage of a property of parallelograms. And that is, if we have a parallelogram, if we imagine this triangle right here that's formed by two of the sides, it's going to be identical to this triangle. And so one of the things that you need to be thinking through to be able to understand how to put this a parallelogram on the coordinate plane is, why are those two triangles congruent? And it has everything to do with slope. The slopes are the same, thus the amount you go up and the amount you go over must be the same. And so those are going to be the same. So what we're going to say is we're going to let the distance, and there's two different ways you can do it. The way we're going to do it is, actually call this 2a, sorry. If we call this distance here 2b, then c, the x coordinate, is going to be the length of the side plus this length right here. And so it would be 2a plus 2b. Because there's some distance right here that is going to get us all the way out to point C. And then our height is just going to be 2c. We don't know how high it is, and so we've got to introduce a new variable. It's not connected to the a or the b. And then when we go over here to d, well, if this length right here was 2b, then that means this length right here is also 2b. So that means the x-coordinate of d is simply 2b. The y-coordinate is the same because of the parallel lines. And so it just turns out that the coordinates of a parallelogram, when you put them on the plane, are 2a comma 0 for b, 2a plus 2b, where 2b is this length right here, the same as this length, comma 2c, which is that height, the distance between those two parallel lines. And then, because we know this is 2b, our x-coordinate of d is 2b. Now, the other way you could have done this one is, instead of having, and so if this was 0, 0, and then 2a comma 0, if you would have wanted this one to be 2b comma 2c, that means the distance from the x-axis to here is 2b. But we know this length is 2a, so this coordinate would be 2b minus 2a. Because if you subtract this whole length, take away the length from here to here, what you're left with is the length to that point. And so that would be another way to do it, but I find this way, the first way, to be easier.